It keeps us warm. It keeps us cool. It protects us. As simple as double-paned glass, or as complex as the shell of a space station. It's all around us, but it's almost always out of sight. It's an essential part of almost every building we inhabit. Now, insulation on Modern Marvels. It's the secret weapon in the war on energy consumption. With a worldwide energy crisis upon us, scientists and contractors are scrambling to design and build more fuel-efficient buildings. Energy-saving insulation is key to winning any battle waged at the fuel pump. Revolutionary products like ICFs, or insulated concrete forms, are changing the way we're constructing 21st century buildings.
Think of them as Lego blocks for big kids. They snap together like Lego blocks. They provide a superior insulation envelope for buildings, homes, schools, churches. They also provide an air barrier and high soundproofing.
The primary insulation material of the forms is rigid foam.
The white part that you see is typically expanded polystyrene made from a base product called styropor. It looks like sugar. It's a sugar plastic. The forms come with a diamond on the top and a circle on the bottom. So the diamonds typically go up and the circles go down. You snap these together, they snuck right in. And you can see this horizontal seam right here. That's where the two have sucked together and it's become an interlocked system.
Next, the blocks are hooked together and fitted with rebar in preparation for the concrete pouring part of the process. The concrete is poured using a boom pump.
It comes down into the hose. We pour about 1.5 to 2 blocks at a time. That's typically about 32 to 36 inches.
Once completed, the building has a double layer of insulation built right into its structure. The insulated concrete forms make it much more efficient than traditional insulation processes.
To make the analogy, if you have a really hot cup of coffee that's poured into a styrofoam cup, you're able to hold on to that cup. And the reason why is because you've got a very thin layer of foam between you and that scalding cup of coffee. If you take that into context of that thickness of styrofoam cup versus this thickness, multiplied twice as a wrap for your building, you get a sense of the incredible insulation values that you're giving yourself to protect from the external environment.
This efficiency immediately registers on the building's energy bills.
The #1 consumer of energy on this planet is to heat and cool structures, to keep humans comfortable in. And with an insulated concrete form envelope in that building, you're conservatively cutting that energy usage down by at least 30 to 40% versus wood frame structures.
Today, ICFs are among the fastest growing insulation products. ICFs have the same goal as all forms of insulation: to effectively control heat flow by trapping air. In a typical 3-bedroom house, 25% of heat is lost through an uninsulated roof, 15% through uninsulated floors, 25% through windows and doors, and 35% through uninsulated walls. Effective insulation can put an end to these losses.
Insulation is basically just a material that slows down heat flow. So that means it can be used to prevent heat from flowing into an area that you want to have cool or flowing out of an area that you want to keep warm.
Heat energy transfer takes place in 3 ways: conduction, convection, and radiation. Conduction carries heat through molecules that are in direct contact with one another in an object, like a metal poker. Convection transfers heat by physically moving molecules from one place to another, such as when warm air rises. And radiation carries heat in the form of waves through space, even if the space is a vacuum. Effective insulation controls all of these heat transfer methods. Today, insulation is a $22 billion a year industry. Modern insulation products are a quantum leap from those employed by early human beings.
Insulation going back in history probably originally was clothing that people would wear, whether it was a skin or a coat made out of animal fur, that type of thing. And insulation in their homes was probably just the the roof of the cave over their head or something real crude. As time went on, people started to figure out how to put more material between them and the outside environment. It may have been leaves or grass in some of the early structures.
Earth itself is a millennia-old form of insulation.
The Egyptians used underground chambers to stay cool, and that was a wonderful way to keep cool, and using the Earth's mass as its own regulated insulator.
Surprisingly, asbestos was an important early insulation material.
Asbestos is a naturally occurring fiber within the minerals of the Earth. It's up to debate really who first used asbestos, but it's guaranteed that the Greeks were the first to actually name it, and that Greek translation was not extinguishable.
All cultures searched for building materials with tiny enclosed spaces in them to reduce heat flow. In Spain and Portugal, the favored material was cork.
It was probably the first renewable insulation product because once a cork oak tree reaches the age of 25 years, the bark can be skinned every 9 to 10 years. It'll replenish itself, but that cork, having that cellular structure, is an excellent insulator.
In Arctic regions, snow was used as insulation.
The Eskimos found that dry snow has millions of entrained air cells in a snow capsule, and so they actually built snow blocks for their homes, which also became an excellent insulator because of the air that was trapped within the snow.
Inhabitants of tropical climates used materials generated by volcanoes.
In Hawaii, I think you'll find probably one of the first uses of mineral wool insulation, and what that actually started from was a mineral fiber, and it was naturally created by the volcanoes. When steam was released from the volcano, it actually turned the lava into fluffy fibers, and they found they could mix that into mud and other products to create their own insulation mass.
In the 16th and 17th centuries, when building construction evolved from solid walls to framed walls with cavities in them, people began filling the cavities with everything from corn cobs to sawdust. With insulation, necessity was the mother of invention. During the 19th century, American homesteaders on the plains used sod to insulate their houses, a practice that continued into the early 20th century.
Folks have been very resourceful in what they want to use for insulation. Many times it's just whatever they had on hand.
Thatched huts in northern Europe were built with a roof of woven straw up to 2 feet thick and walls of straw and clay. It wasn't until the Industrial Revolution in the 19th century that deliberate commercial applications of thermal insulation became mainstream. Mineral wool became one of the most popular products.
Mineral wool is a very broad definition. It basically covers any type of insulation made from glass, rock, or slag. And I think that you found all these, I guess, new technologies becoming much more popular after the Industrial Revolution because of the processes that allowed easier access to these.
Molten slag was a byproduct of the iron ore blast furnace. Iron workers found that injecting it with steam accelerated the cooling and solidification process. This acceleration expanded the structure of the slag, producing fluffy fibers that could be turned into mineral wool. In the early 20th century, builders also began to use specially designed insulation boards. These were created by processing wood, cane, or vegetable chips into a pulp that was pressurized into boards. In the 1930s, the insulation industry developed a wonder called fiberglass. The technique of heating and drawing glass into fine fibers has been known since ancient times. However, the first glass fibers of the type we know today as fiberglass were made by accident. In 1932, Dale Kleist, a researcher for Corning Glass, was trying to weld together two glass blocks when a jet of compressed air inadvertently hit a stream of molten glass and created a shower of glass fibers. The resulting spray of fine fibers turned out to be very light and very strong. In 1935, Corning Glass joined forces with Owens, Illinois, to develop the idea further. Research showed that glass was a poor conductor of heat, and tightly woven glass fibers trapped air. With its ability to do both of these things, fiberglass proved to be an excellent insulator. Today, Owens Corning is one of the largest fiberglass insulation producers in the world. The whole process of creating fiberglass insulation begins with the traditional batch of materials used to create most forms of glass.
We're behind an electric melt cold top furnace. This furnace is melting the batch materials. Those materials have about 50% sand, about 40% recycled plate and bottle cullet, and about 10% soda ash, limestone, and borax. These materials are melted underneath from the batch cover by electric heating. It's a temperature around 2,400 degrees. And then the glass flows out into the channel towards the fiberization process.
The temperature of the glass is tightly controlled within tolerances, as well as the flow rate of the glass as it is entering the fiberization process, which is essentially a spinning process, very similar to a cotton candy machine.
Owens Corning makes pink insulation. The color pink is actually a registered trademark of the company. It uses the color to visually distinguish its product from other brands.
After the liquid glass is spun into fiber, we spray on a resin. This fiber and resin and dye is collected onto a conveyor, which feeds into our curing oven.
Fiberglass insulation is so soft because the fibers themselves are 20 times thinner than a human hair, making them flexible and resilient.
After the material is cured in the oven and the thickness is set, the fiberglass pack is conveyed down the line to the fabrication area. Behind me is the chopping area where we are cutting the bats to length to meet the various product specifications required by our customers. Here we are in the bat packaging area. We are mechanically compressing the bats to remove the air and reduce the overall volume of the package. This is really an important step in being able to store more material in our warehouse, as well as to enable easier shipping and handling to our customers. This is the end of the line. The time it took from when the liquid glass was fiberized until it got down here in a finished bat bag was less than 5 minutes.
The assembly line at this Owens Corning plant often runs 24 hours a day and produces enough fiberglass to insulate almost 175,000 homes per year. Today, fiberglass insulation comes in many different forms. One of the most popular is bats, which are pre-cut to a specific shape and thickness in order to fit in the standard framing of a building. Another very effective form of fiberglass insulation is Johns Manville's spray-in spider insulation.
When applying spider insulation, you'll see the installer with a blowing hose which will lead back to a blowing machine where the loose fill fiberglass has been placed. It'll be ground up and conveyed through the hose to the nozzle. There'll also be a line delivering tacky adhesive, and that'll be mixed at the nozzle. He'll direct that material mixture into the wall and work the nozzle back and forth to build up the insulation to fill up the whole cavity. His assistant will come along behind the sprayer with a scrubbing tool, a roller that he'll run down the face of the studs to scrub off any excess to leave a nice flat layer right at the front surface of the studs. The adhesive used with the insulation will quickly solidify and dry, and the wall is ready for finishing with drywall almost immediately. Then any excess that's remaining on the floor will be vacuumed up and it will be recycled back into the hopper, where it will be sprayed into the wall again further down the line. So when you're done with the job, there's no waste, no leftover material.
Another kind of fiberglass insulation, especially useful for insulating attics, is loose fill.
Loose fill is blown using a special machine through a hose into an attic area or sometimes into a wall. It basically stacks up and fills that area with insulation. The advantage of a loose fill insulation in an attic, for instance, is that it'll fill in around all the gaps and cracks around framing and other obstructions that might be up in there.
The name of the game in the insulation business is filling any holes that allow thermal energy to escape. One extremely effective substance starts small, but grows to get the big job done: foam. The Trans-Alaska Pipeline is wrapped with 4 inches of fiberglass insulation, which keeps the oil warm while it flows 800 miles to a refinery. Insulation will return on Modern Marvels. It's pumped up, it's gooey, and it's one of the best insulators available. It's foam. Foam products come in many forms. One of the most effective is spray. The process of spraying foam insulation is almost an art form. It takes a steady eye, a sure hand, and a definite sense of rhythm. Foam is an exceptional insulator for roofs.
Roof insulation foam offers significant advantages over alternative materials. It forms a seamless membrane which stops leaks. The material flows into cracks, crevices, expands, and seals up all the leaks. It also offers much more insulation value versus alternative materials. And the fact that it's soaked into all the cracks and crevices and cured means that it's gluing everything together, so it's going to be able to withstand significantly more harsh weather conditions than a typical roof would.
The key to making a smooth urethane application when we're talking about roofing is to overlap each previous pass by 80 to 90%. When you're spray painting, normally you'll think about a 50% overlap. When spraying urethanes, you think of 80 or 90%. Because urethane expands 30 times its liquid form, that becomes critical if you want to get a smooth application.
The idea of surrounding a building with a complete envelope of insulation like foam has been growing since the 1920s, when the way we constructed buildings began to change.
Prior to the 1920s, even going back to the Victorian age, you found that homes were constructed of heavier, denser materials. A lot of that was just the prevalence of old-growth forests that were used for framing. By the time the 1920s rolled around, we found that materials were becoming lighter so they could be constructed more quickly, but there also became a greater emphasis on the idea of the thermal envelope of a residence. You start to insulate the floors and the walls and the roofs.
The use of building insulation was first made mandatory in the United States during World War II to conserve fuel for the war effort.
You all of a sudden had to start being more concerned about conserving your energy resources, whether it be oil or gasoline. And because of that, they looked at better applications of insulation. That same example was driven home in the 70s. People reacted to oil prices and gas prices and energy prices going up. The 1970s saw the advent of the idea of the super-insulated home.
Foam is a substance that is formed by trapping many gas bubbles in a liquid or solid. One of the most popular foams is polyurethane. Originally developed during the 1940s for military and aviation applications, it began to be used as insulation during the 1950s. In the 1970s, innovators began spraying the material. Polyurethane is made of several key ingredients.
These are the materials you see stored in the large tanks behind me. This is a polyol. It's based on sucrose or sugar in petroleum products. This is a surfactant. Surfactant controls the size and the shape of the bubbles. This is a catalyst which controls reaction rate. The quicker the reaction, the smaller the bubbles.
The size of the bubbles is important because it dictates the density of the foam. Roofing foam, which might be walked on, needs to be stronger and denser than wall foam, which is rarely touched after it's applied. All of this is factored into the formula when a batch of foam material is mixed at the factory. But where do the bubbles come from? The blowing agent.
Blowing agent is a liquid that has a low boiling point. When it's spray applied, it converts from a liquid to a gas, forming the bubbles.
These four ingredients are mixed together into one liquid, but they're only part of the recipe for making foam. The other part is a substance called isocyanate, a highly reactive molecule. It's separated from the other ingredients until the spraying begins.
They're dispensed separately all the way through the hoses to the gun. When the applicator pulls the gun, the materials are mixed together, the reaction occurs. It hits the substrate in a liquid form, but the reaction drives the expansion very, very quickly. Within seconds, you've got cellular plastic.
Isonine is a foam insulation that's used to create an envelope of protection around a building.
We come into a house, we will seal around the doors and the windows, we will plastic everything off, and then we will spray the entire house. We'll spray the walls, the floors, and the roof deck, and completely encase the house in foam.
A properly insulated house can save a homeowner a great deal of money.
The consumer today is better educated as far as the value of better insulation in their home. What they have learned is they can pay a little bit more on the front end to better insulate their home, but they will recoup savings in the long term versus their energy costs because their house is better insulated.
Today, insulation-savvy home and business owners are finding that there are savings to be gained from insulating not only the walls of a building, but the windows too. Each year in the United States, nearly $13 billion worth of energy in the form of heated or cooled air escapes through holes and cracks in residential buildings. Insulation will return on Modern Marvels. Designers of today's superstructures strive to insulate every important section. One critical area includes the windows. There's little to be gained from insulating the interior walls and ceilings of a structure when all of the thermal energy passes easily through the windows. At the Lawrence Berkeley National Laboratory in Berkeley, California, scientists are working to develop windows with superior insulating properties. The lab is managed by the University of California. One major advance in window insulation came with the introduction of double-paned windows.
For centuries, single-pane glass was the standard in buildings throughout the country. However, in the 1960s, window manufacturers began to experiment with and develop insulating glass, which are two pieces of glass separated at the edges by a spacer with the airspace sealed from the outside so that no moisture can condense between the two pieces of glass. Insulated glass became much more popular in the United States after the early 70s energy crisis. This is a standard double glazed window, which means that it has two pieces of glass. The two pieces of glass create a dead air space, and it's that air that's really the insulator in this window system. Air's thermal conductivity is very low compared to other solids, which means that the rate of heat flowing through it is low. That's why it's a great insulator.
To further improve the glass's insulation qualities, manufacturers added a low emittance coating to reduce heat flow through it. Air is a good insulator, but in the 1980s, some manufacturers began filling their panes with heavy gases, such as argon.
Air is a good insulator because the molecules that comprise air, nitrogen and oxygen, are relatively large, simple molecules. Molecules transfer energy from one molecule to another through colliding with each other and transferring energy with those collisions. Bigger molecules like argon move slower, and so the rate at which they transfer energy from one molecule to another is lower, and therefore their conductivity is lower. The rate at which the whole space transfers heat is lower.
In the Berkeley labs, each new glass insulation design is run through a battery of tests.
This is our window thermal test facility. If you look back there, you can see two windows framed in red. Those windows separate this warm side chamber from a cold exterior chamber. And with our special imaging equipment, we can look at the surface temperatures of these windows. Now, by understanding what the surface temperature patterns are, we can tell how good an insulator the windows are.
Scientists also use infrared tests.
With this infrared camera, we see the infrared radiation that is one of the forms of heat transfer. It can tell us the performance of a thermal insulation by side-by-side testing, such as with these three windows. Here we have a single pane of glass, a poor insulator. You can see its temperature is very cold because the color indicates the surface temperature. Here we have a double pane of glass separated by airspace that's a better insulator, and best performing triple paned insulating glass is up here. The different colors you see in the infrared image represent different surface temperatures, which is an indication of the performance of the glazings.
A major breakthrough in insulated glass was the development of gas-filled panels in the 1990s.
We realized that the same principles that were being used to create highly insulating windows could be applied to creating a high-performance thermal insulation that was lightweight and that utilized a small amount of materials. This is a gas-filled panel developed here at Lawrence Berkeley National Laboratory. And here is a similar panel with the edge cut away so we can see the inner workings of the gas-filled panel. This material here is called the baffle. It creates numerous gas or air-filled spaces. These small spaces are effective at reducing the transfer of heat.
The panels have many uses, including insulating automobiles, food containers, and buildings.
This is an example of a gas-filled panel that's been developed for use in buildings. This particular product here is designed for use in attics, and it's meant to augment existing ceiling insulation that might not be quite enough insulation for today's homeowner. This product comes from the factory in an uninflated state so that it's very thin and can be transported easily. And to inflate it, you simply take an air compressor or some form of compressed air and inflate it.
Most insulation is hidden from sight. It works silently and rarely draws attention to itself. Yet it must handle heat, cold, smoke, fire, and even acoustic variations. The only way manufacturers know their products are up to the task is to test them elaborately and dramatically. A gas-filled panel that is 1 inch thick can provide the same insulation performance as foam that is 2 inches thick. Insulation will return on Modern Marvels. The purpose of insulation is to create a comfort zone in a building. Usually out of sight, concealed in the walls of a structure, insulation rarely crosses the minds of a building's inhabitants. Like plumbing and wiring, it's taken for granted until something goes wrong. Insulation manufacturers like Johns Manville strive to eliminate problems by testing every aspect of the material before it goes on the market. For instance, insulation is tested extensively to see how it reacts to fire.
The ASTM-E84 test is designed to measure the surface burning characteristics of building materials. What we do is we start a flame across the face of a building material, whether it's plywood, insulation facings, and we measure how long it takes for the flame to propagate across the surface of this material. we're also doing simultaneously is measuring the amount of smoke that comes off of this material as it burns. One of the things that we're concerned with is that as things burn, they give off smoke, and smoke is just as hazardous, if not more so, than the fire itself. We do this test method to make sure that the products that we manufacture are going to be safe for their intended use.
Testing helps manufacturers, like Urethane Contractor Supply and Consulting, develop the right insulation for any job.
UCSC invested in an extreme conditions test lab to test adhesion and other physical properties of our spray foams on very cold substrates, including concrete. And we've made significant improvements in our adhesion and other physical properties of our products. For example, in the Midwest and the Northeast, in the spring, residential construction starts, they pour the basement. The basement walls are very cold, typically 30 or 40 degrees. Traditional spray polyurethane foam materials don't adhere well in that application. Our Polar Pro is engineered to adhere to very cold substrates.
Insulation is also tested to determine its R value. This is a government-required rating that indicates a product's insulating qualities.
R value is a standard term that means resistance to heat flow. R value is the principal way of explaining the performance of insulation. Every home insulation product is rated through standard testing with a certain R value, so a consumer can compare one product to another in standard terms. So the higher the R value, the more resistance to heat flow that the insulation is providing.
Researchers also perform elaborate tests on an insulation's acoustic properties.
When we talk about insulation, we don't have to talk only about thermal insulation. There's also acoustic insulation. This is very important in hotels, hospitals, when there's an element of privacy that's required.
Acoustics are very important. If you look at the way we're building now with property values going up, the increase in townhomes, condominiums, you're very concerned about noise between units.
Acoustic engineers at companies like Johns Manville often strive to include both thermal and acoustic properties in the insulations they produce.
Acoustical insulation and thermal insulation, they're very similar in the fact that they're made the same way, they're made on the same production line, and a lot of ways they do the same thing. What's good for sound a lot of times is good for thermal and vice versa.
A specially designed reverberation room allows engineers to bounce sound off their products from every angle.
When we walk through the door of our reverberation room, what we see is a lot of diffusers on the wall. There's a large rotating vane that's on the upper portion of this room. What we're doing is we're trying to create an environment where the sound pressure level throughout the room is going to be even no matter where you're listening.
Sound is a series of waves created by the vibration of an object, like a loudspeaker. Some insulating materials absorb sound waves by converting them to heat, which is produced by the friction of the vibrations passing through tiny openings in the material. One important test performed in the reverberation room measures the amount of sound reduction an insulation product can deliver.
How we test our material is that we place it inside the cavity of a wall. We put this wall in between two rooms. We energize one side of the wall with 100 decibels of sound, and then we measure how much of that sound goes through to the other side with another microphone.
The technicians call the 100 decibels of sound pink noise. It's equivalent to hearing a jackhammer from just 6 feet away.
Pink noise, if you can imagine a spectrum, you have frequencies range from 100 hertz all the way to 4,000 hertz. And at each one of those discrete frequencies, we have 100 decibels of sound. That way, when we're looking at the difference going from one side to the other, we know we're always starting at 100, and we know that that sound is going to be reduced going from one side of the wall to the other.
Another acoustic insulation testing room is anechoic, meaning it permits an unusually low degree of reverberation.
What you see as you walk into our anechoic room is that the walls have fiberglass wedges on the walls. What these are designed to do is absorb all the sound in this room that radiates from whatever noise source that we're trying to measure. The advantage of this room is that we're using two microphones so we can measure not only the magnitude or the amount of sound coming off of whatever we're measuring, but we're also measuring the direction so we can make a map of sound that's coming off of this device. In this case, we have an appliance, and what we see is that We know that we don't get a lot of noise coming through the door, but we get a lot of it that comes out from underneath. Unfortunately, we need to have airflow underneath this device to make sure that it's cooled properly, but again, that's also a path for sound to come through. This gives us a way of finding how much sound is coming out from what part of this assembly.
Once the sound is mapped in these rooms, the insulation can be altered accordingly to improve acoustic performance. We require different types of insulation to keep our homes comfortable here on Earth. But what if home is in outer space? Anechoic chambers can absorb 99.9% of sound. Because most ambient noise is eliminated, people have reported hearing their own hearts beating and blood flowing while inside a chamber. Insulation will return on Modern Marvels. Insulation is helping us go places we could never go before, including extreme environments. When designing insulation for the International Space Station, scientists were confronted with a set of problems found nowhere on Earth.
We don't have the benefit of Earth's atmosphere when we're in orbit. And not having that benefit, we're exposed to much more extreme environments. In the same orbit, we can see temperatures in excess of 250 degrees Fahrenheit while we're in the sun, while a few minutes later be exposed to conditions that produce environments less than minus 250 degrees Fahrenheit. And we go through this 16 times a day, every day, 365 days a year.
Scientists had to rethink the entire insulation process when designing the station. The rules that govern air and heat movement on Earth simply don't apply in outer space. The Earth's atmosphere allows heat to be transferred by convection. But in space, there is no atmosphere. The vacuum of space allows only for radiant heat transfer, usually in the form of energy waves emanating from the sun. Earth's atmosphere prevents it from being overheated by these waves. But the space station, without such protection, is subject to the extreme temperatures brought on by solar radiation. The scientists had to come up with an insulation that would safeguard it. Their solution was a multi-layer insulation, or MLI.
MLI serves two purposes. The first is to reject or reflect a lot of the sun's energy, and the second is to entrap heat that's generated internally. And by doing this, we can moderate the extremes that we see on orbit.
One of the key components of the insulation is the plastic, mylar.
On that plastic, we apply thin layers of aluminum, which is your typical aluminum can type of material. And that aluminum is very reflective.
The mylar is protected by an outer layer of fiberglass fabric called beta cloth. This layer strengthens the insulation blanket. The inner side of the beta cloth is aluminized to prevent harmful radiation like ultraviolet light from drying out and cracking the mylar layers beneath. The next layer is a fine mesh fabric of Dacron. This prevents the conduction of heat between the aluminized layers of mylar. There are at least 10 more layers of aluminized mylar and Dacron per blanket. All the layers are sewn together to create a pillow-like blanket just 1/4 of an inch thick.
I'm going to show you a little bit about the multi-layer insulation that's installed on the space station right now. Here we have examples of large blankets which cover the end cone of the space station. Now they're held on with these little tiny buttons or grommets with some lacing thread. And now this acts to actually not conduct heat down to the skin of the space station itself.
When designing the insulation, scientists also had to make sure it didn't weigh too much.
We use very thin layers to make up multi-layer insulation. And the reason mainly is because of weight. The pressure shell of the module itself is about 1/4 inch thick on some of these modules, and that aluminum can be very heavy. Well, the last thing you want to do is add more weight to the space station.
The insulation also had to be designed to be tough, because unlike most insulation on Earth, space station insulation takes a real beating.
The space environment is very hostile. We have micrometeorites that pound the space station at all times. Here's an example of the meteoroid debris shield, which actually takes the hit from meteoroids to prevent the multi-layer insulation from being damaged.
Working in tandem with thermal controls inside the station, this advanced insulation helps to maintain a stable onboard environment. With a temperature of 65 to 80 degrees Fahrenheit and humidity in the range of 25 to 70%. The extreme environment of outer space is approximated on Earth, at the bottom of the sea. Again, insulation is a key component, especially in the design of protective gear worn by divers. One of the first diving suits was introduced in 1837 by Augustus Sieb, a German engineer. Early diving suit makers were much more interested in making their suits waterproof and easily supplied with air than insulated for the diver's comfort. However, as diving equipment became more sophisticated and divers stayed underwater for longer durations, the need for insulation grew. Without it, the cold water could seriously affect a diver's performance.
He's going to fatigue a lot quicker because now he's shaking and shivering underwater. He's going to lose a little bit of his mental focus.
Today, one of the most common diving suits is the membrane dry suit. Heat insulation is provided by the clothes a diver wears under the suit. These garments are often similar to those worn by skiers and mountain climbers in cold climates. As the name indicates, the suit keeps a diver dry after it's sealed at the neck and wrists. No water touches his body.
This is the inner garment that's worn by the diver. It is referred to us as a woolly bear. It's a fleece-lined down suit that goes close to the diver's body and provides a layer of warmth between the diver and the outer garment, which is the dry suit.
The wetsuit is another form of dive suit. It was made possible by neoprene, a stretchable and buoyant synthetic rubber invented in the 1930s. The first wetsuits were marketed in the early 1950s.
The neoprene wetsuit works by trapping a layer of water between the diver's body and the insulation material, which is the neoprene. This particular wetsuit is 5 millimeters thick, so there's a 5 millimeter layer insulating the diver from the ocean, then the layer of water, and then the diver's body. The diver's body warms the layer of water inside the suit, and that's what keeps him warm.
For extreme dives to depths of 2,000 feet beneath the surface and temperatures near freezing, divers rely on the hard suit. The suit itself has no insulation, so the diver must wear special gear.
The hard suit is much like a miniature submarine. The diver will get in and wear this thing like a suit. It has arms and legs with mechanical joints, and he's protected from the environment by an aluminum suit, but he's not protected from the environment for cold. He has to wear additional insulation inside the hard suit. A hard suit diver will be insulated by up to 4 layers of protection, depending on the temperature of the water and the amount of time he's going to spend in the water. He starts with a polyester and spandex undergarment that wicks moisture away from his body, so that as he works, if he develops sweat, that moisture is wicked away from his body. Follow that with a typical dive skin, which is sort of fleece-lined and has a little bit of a neoprene-type covering. And then he's got a fleece-lined Gore-Tex-type Arctic jacket, which provides the bulk of the insulation from the temperature, keeping his body heat in. And then finally with a completely watertight Gore-Tex outer garment that prevents moisture from getting in but allows his body to wick out, to breathe out.
Whether beneath the sea or on a space station, insulation has always helped us create comfort zones. At home or in the office, it's essential for making our world habitable. How we use it and how we develop it will be of major importance in how we conserve our supply